Get ready to blast off into the incredible world of brain-computer interfaces. Neurocareers doing the impossible is taking you on a journey to meet the fearless pioneers pushing the boundaries of what's possible. In this special series, we'll be shining a spotlight on the nominees and winners of the International BCI Award, one of the biggest and most prestigious awards in the BCI world. You'll hear from BCI professionals as they share their revolutionary work and get a behind-the-scenes sneak peek at what it takes to be a winner. So, buckle up, grab a snack, and get ready to be amazed as we explore the impossible becoming a reality in the world of BCIs. But before we blast off, I want to give a big thanks to the co-host of this BCI Award edition on our podcast, Dr. Christoph Guger and GTech Medical Engineering. When I was a faculty member at the University of Cincinnati and Cincinnati Children's Hospital Medical Center, my team and I did some pretty amazing stuff for patients needing epilepsy surgery. We would put special sensors, also called grids, directly on their brain to prepare for surgery and create maps of their brain in a much faster and safer way than is usually done. It's called high gamma mapping, and it lets us figure out in just a few minutes the essential parts of the brain that need to be spared during surgery. Can you imagine? You can create a map of language, motor, and even math processing in no time. It was the first time this innovative technology was used at Cincinnati Children's Hospital Medical Center. When I moved to Florida, I established the first functional brain mapping and BCI program at Florida Hospital. I continued to use high gamma mapping to help epilepsy patients avoid losing their ability to speak or move after surgery. But even cooler than that, I created brain-computer interface studies that let patients control things with their brain in real time. Our patients could even spell words with incredible speed by just using their brains. No hands involved. I also discovered that brain-computer interfaces could help patients move their chronically impaired hands or legs years after a stroke when not much else could help them. So, I started working with the faculty from Advent Health University to help these patients restore their ability to use their hands. I received special training for it, and it's still mind-blowing how cool it is. My favorite part of what I do is teaching. At my established Institute of Neuroapproaches, I've integrated all my experience and knowledge into a unique course on brain-computer interfaces. With graduate neurobiology students, we started with theory, and then I gave them the BCI equipment so they could have hands-on experience working with BCIs. It significantly improved the way students learn, and they absolutely love this practical part of learning how to use neurotechnology. And all of this was made possible thanks to GTech's awesome brain-computer interface technology. They have everything from high-tech up to 1024-channel EEG systems to wearables, tools for neurorehabilitation, such as the medical grade system recoveries and educational kits with unicorn hybrid plug for learning how to work with BCI technology. But the most important part is their support and care. I have enjoyed working and collaborating with Dr. Christoph Guger and GTEC employees for over 15 years, and I hope for many more successful years ahead. So, if you are interested in GTEC's brain computer interfaces and neurotechnologies, check out their website at gtech.net. It's worth it. And keep in mind, I do not receive any financial support from GTEC and share my honest opinion supported by many years of experience working with their equipment. Dear Neurocareers podcast listeners, are you ready for another exciting adventure of the BCI Award Neurocareers podcast series? Today, we have a special guest that you absolutely cannot afford to miss. His name is David Moses, PhD, and he is a postdoctoral scholar who is at the forefront of developing speech neuroprosthesis to help people who are unable to speak due to paralysis or other conditions. David and his team won second place in the annual BCI Award 2021 competition for their groundbreaking work on speech decoding directly from the human brain. David is currently working at the University of California, San Francisco, in Dr. Andy Chang's lab, where he is pushing the boundaries of what's possible in the field of speech neuroprosthesis. So, if you are fascinated by the world of brain computer interfaces and how they can help improve people's lives, get ready to be inspired by this special episode of the BCI Award Neurocareers podcast series. Tune in to hear David's motivating story and see an example of a successful BCI Award submission that can help you take your career to the next level. Are you ready to dive in? Let's do this. Welcome, David. Thank you so much for joining us on this podcast. We very much appreciate this. Can you give us a brief introduction and let our listeners know where you are joining us from, your background, and maybe you can share some interesting facts or information about the lab you are working at, the history behind it, and maybe some main areas of research in it?
Great. Thank you, Milena, for having me. It's my pleasure. So I am in San Francisco, California, in the USA right now. I guess a little bit about my background. I got my bachelor's in bioengineering from Rice University in Houston, Texas. Right after getting that, I went to get my PhD in bioengineering from the joint program between UC Berkeley and UCSF. And during my PhD, I joined Dr. Eddie Chang's lab at UCSF, and that's where I'm still at now as a postdoc. So I've been in the lab for a long time, and I can definitely give you a little bit of its history. Yeah, I think I'm the second most senior member of the lab in terms of time. Eddie's number one, of course. And then there's one other person, Matt, who's great, and then me. So let me give you a little bit about the history. So the lab's main original focus was on speech neuroscience. Our PI, Eddie Chang, is the head of neurosurgery at UCSF now. But back when he started, he was a prominent neurosurgeon who started a research lab to see what we can understand from patients who come in for epilepsy. So they have intractable epilepsy that's uncurable by medication. And so they have to seek treatment via surgery. And so they get a sheet of electrical sensors that's implanted on the surface of their brain. This is called electrocorticography, or ECOG for short. And so the goal of these sensors was to find where the seizure was originating from and to understand how the seizure progresses anytime they have a seizure, so that they can guide a neurosurgical treatment. For example, resection of the tissue that is causing the seizure. And while these patients are being treated with this approach, Some of them volunteer to participate in studies. So we've done speech studies where they listen to things, say things, etc., while we record their brain activity. And this is how we gain a very precious view into the human brain to answer these research questions that would be really difficult to answer otherwise. And that's kind of where the lab started, but now the lab has many research interests from epilepsy to emotional processing, neuropsychiatric disorders to chronic pain, but still a very large focus on speech as well. And my project personally in the lab is kind of as the lead postdoc, kind of like a project manager and coordinator for this clinical trial that we have ongoing called the Bravo clinical trial. And in this trial, we've learned a lot about speech with our epilepsy volunteers. We've learned how certain sounds are represented in the surface of the brain and neural populations scattered throughout what we call the speech motor cortex. We've also learned how we can take these signals and decode what someone is saying. So when an epilepsy volunteer who is an able speaker says something, we can actually decode what they said from the brain activity. It's not perfect, but it works quite well. Now, the purpose of the Bravo clinical trial that I just mentioned that I'm working on is to see if we can translate this technology to people who are unable to speak. So we work with patients with severe paralysis. So these patients, for example, our primary patient, or our first patient, Bravo 1, who's also known as Pancho, there was some New York Times article written about him. I actually have a picture of it on my wall here. Maybe a little bit hard to see, but we're really proud of that story and of him especially. He had a brainstem stroke, and then he volunteered to participate in our clinical study. So he's unable to speak or type. And we have a brain implant that, similar to what I described for the epilepsy volunteers, it's a sheet of electrodes that we implanted on the surface of his brain. And through the electrical signals recorded from this implant, while he tried to speak, we were able to decode what he was attempting to say in a very limited and proof of concept application. But we still showed for the first time that this was actually possible. If someone who hadn't been able to use speech to reliably communicate for 15 years still had these really robust representations of speech in their speech motor cortex. And we were able to use those signals to decode what they were trying to say. And so that's kind of my role in the lab, is carrying on that clinical trial research as we pursue new research questions and new directions to improve the technology and to understand more. And I realize this was probably a long answer to your question, so I'll pause here.
But this was a very interesting answer to my question. Thank you very much. And what inspired you to pursue research in this field of neuroprosthetics, speech, specifically neuroprosthetics?
Yeah, that's a great question. And sometimes I look back and maybe some combination of just luck and also knowing that I needed to explore my options. So to expand on that a little bit, when I first started my undergraduate studies, I was computer science only for like a week or two. Then I realized that for me personally, I wanted to do something with a clinical application, but I still really, really liked computer science. In high school, I was on the computer science team. I liked programming. I liked quantitative problem solving. I liked engineering. So I felt like bioengineering was a really good, not necessarily a compromise, but a synergistic field of study where I could have the ability to hone my skills and expertise in all the fields that I was interested in engineering and programming and in things related to something that could be an application to help people one day. And so in my junior or senior year, I really started to get more and more interested in the brain and trying to understand, the final frontier, if you will. It's just so interesting, everything about the brain to me. And I was really motivated to learn more. And that's why when I applied to graduate school, I was sure to pick out schools that had a really good neuroengineering focus, because that is something that I'm very interested in, brain-computer interfaces and things like this. But I didn't know exactly what I wanted to do. And that's why I mentioned that remaining a little bit flexible, if you will, was really important for me. And that's why the UC Berkeley UCSF program felt like a really great fit for me, because I was able to do a year of rotations. And that's really important. Not a lot of PhD programs, well, I don't know what the split is, but not all PhD programs offer that. but I knew I couldn't just join a PhD program and join a lab because I was still a little undecided. So I started at UC Berkeley, started to do my rotations, and then there was this class by Dr. Jose Carmena at UC Berkeley, where it was kind of like a seminar series where a lot of different professors would come and describe their research. Each week or whatever, they'd give a presentation about their research so we could learn more about what their lab does. And this is when I first learned of, Dr. Eddie Chang's research. And I never considered speech as a potential modality of interest for brain-computer interfaces. I just not thought of it. I hadn't considered it. I was really focused on the arm reaching and limb motor prosthetics type applications. And so for me, this sounded really, really interesting. And I reached out a few times and Eddie let me rotate in the lab. And then from there, that's kind of how I kept building on this. I started with some engineering projects with the epilepsy volunteers to understand what can be decoded from brain activity. That was always kind of my focus of my PhD. And then moving it to real time. So with my current responsibilities, in addition to kind of project management, I'm the primary maintainer of a real-time software architecture that I built throughout my PhD, and this is what enables us to collect all of our data in the clinical trial too. So I had a very engineering-focused PhD, which I really enjoyed, and yeah, that's kind of how I not quite stumbled, but not type razor-focused, ended up in a field of speech neuroprosthetics. It was just kind of a little bit of right place at the right time, and also making sure that I was open to new possibilities.
Yeah, thank you so much for telling this to our listeners about being open to possibilities and also taking time to get rotations, to go to the seminars, to see what's available. Yes, and then choose something that resonates with you most. Thank you. And now, as we're talking about speech neuroprosthesis, can you define for our listeners what do you mean by that?
Sure. First, maybe it's best to explain what a neuroprosthesis is. So, if you think of just a prosthesis, that could be, for example, an artificial limb. For example, a leg, like an artificial leg that someone who's lost their leg can get. It's a static physical device that doesn't really interface with neurons or do anything fancy in that direction. It's mainly meant to kind of replace a missing physical component of the person's body and perhaps other details I'm missing. But the key point here is that it's not a neural interface. And so a neuroprosthesis is any type of prosthesis that also interfaces with neurons. And so this doesn't have to be the brain, for example. It could be EMG sensors, so little electrical sensors, perhaps on the upper portion of your arm that can help restore some kind of control over an artificial hand. The point is just any neuroprosthesis means that it's a prosthesis that interfaces with neural signals to some capacity. And then a speech neuroprosthesis is what we're referring to as a brain-computer interface that can restore the ability to communicate via speech to someone who perhaps has lost the ability to speak. And so I think the clear example is the one from our work where someone suffered a brainstem stroke, lost the ability to articulate speech. So they're not using speech to, they can't talk like you and I talk. And for this person, Pancho, when he tries to speak, for example, he can produce some vocalizations, but they're highly unintelligible. And so for him, speech isn't really a strong communication option like it is for us. And so the speech neuroprosthesis is something that can interface with his brain and the neural signals that would have normally controlled his vocal tract. And this device will bypass his paralysis and decode his attempted speech from the brain activity. That's really the goal of this type of speech neuroprosthesis. Now, in the future, there could be way more interesting types of speech neuroprostheses. For example, this I think is a long way off because we know very little about this, but you could imagine for some patients with certain conditions, you could have a brain-computer interface actually stimulate the brain to reanimate their vocal tract. And so if you were able to figure out they wanted to say hello, you could stimulate the brain such that their articulators move and say hello. And their larynx is engaged and everything works together to say hello so that they're saying it through their own body. I think that is the best of my knowledge, that's still a long way out, but it's not impossible. And that would also could be considered a speech neuroprosthesis. But when we're talking about it today, we'll likely just talk about this more sensing only, just output, no input to the brain. It's just reading signals to bypass paralysis so that someone can try to speak and their meaning is conveyed. Their intended speech is interpreted.
Thank you so much. And can you also explain to our listeners how this speech neuroprosthesis is different from BCI devices that allow people to spell certain letters or numbers or use a cursor on the computer screen also to write things? What's the difference?
I would say the earlier brain-computer interfaces, many of them that have been evaluated in human patients, have used this spelling brain-computer interface setup, like you mentioned. And so this is operated via something called cursor control. And what this means is that you can record brain activity from, let's say, the motor area, such as the hand motor area. So the part of the brain that normally lets us control our hands. And you can actually train someone to use a system where they can use signals from that brain area to control a computer cursor. So this is a two-dimensional space, right? The up-down is one dimension, left-right is the other. And so through some effort, like if I was the BCI user, the brain-computer interface user, I would think maybe I would move my hand to the up left, and then they can get the cursor to move to the up left. And this type of approach can be combined with a spelling board, like a spelling interface, so that someone can point to letters and spell out messages. I think this is a really cool first step, of course. I mean, you're showing that now someone who can't speak or type, for example, can use this to get their thoughts out. It is slow, relatively tedious, I would say, but compared to speech, and that's why we really prefer speech. That's why it's also because that's what our lab has studied. But we just think speech is, there's a reason we're talking right now, right? It's like speech is so expressive and so efficient. It's really this extremely extraordinary mode of communication that humans have developed that, you don't see in other species as well. It's very precious. And I think that restoring speech as a mode of control of a brain-computer interface for communication, that I think everyone in our lab is very motivated that this is the approach that we feel very passionate about, I'll say. I should mention, there was a very cool spelling BCI. Actually, I think it won the BCI award the year before we entered. It wasn't cursor control to point to letters, it was handwriting. So the user was attempting to handwrite, but their hand was paralyzed, so they can't physically handwrite, but they would think and volitionally try to handwrite letters, and they could detect the neural correlates of these handwriting attempts and use that to decode speech. And that was a really cool work as well from the late Dr. Shinoy's lab in Stanford in California as well. And the very last thing I'll say is just this past BCI award competition, we also showed our results for a newly published paper on using speech as a spelling modality. So in our work, and we got third place for that, which we're grateful for. But in this approach, the user is not using cursor control or this kind of two-dimensional control to spell, but they're trying to silently say, for example, NATO code words. So Alpha, Bravo, Charlie. So you would spell something out using these code words and trying to say them. And then that would enable a spelling interface too. So we just wanted to know, can we create a spelling interface of our own through speech? In addition to our prior work that focused mostly on direct attempts to say the exact word you wanted to say instead of spelling it out.
Thank you so much. And we will talk more about what you just said in more detail. But before that, I would like to talk about the extent of the problem that you are trying to address. So you are trying to help people unable to speak for one or another reason. How many people in the world can benefit from this type of research, and what type of problems do these people have? Apart from having inability to speak in common, but maybe some specific diagnosis.
I think it's hard to come up with an exact number for this. So we think that people with amyotrophic lateral sclerosis, so ALS or Lou Gehrig's disease, I think that many of these patients who have this very terrible disease end up losing the ability to speak and also to type. And I think the rates of the incidence rates of this is kind of hard to estimate, but maybe it's around 6,000 per year in the United States, perhaps more worldwide. People with brainstem strokes who have chronic speech disability and motor disability are also, I think, could be very much helped with this technology. Just to preface this, we're at the point now where, because it requires brain surgery, nothing's penetrating the brain with our approach, but you need to gain access to the brain to implant our interface on top of the surface of the brain. Statistics show it's not truly that risky, but it is still a brain surgery, right? So it's not for everyone. And so right now, the people who we think would be most helped are basically those in the most dire need. So these are people who are unable to speak or type. Because if you could type, you would likely be able to use other software to recreate your voice. You wouldn't need to get a brain implant for this. But if you're unable to speak, and if you couldn't type, but you could speak, you could use dictation software to control your computer with your voice through accessibility features. And so you may not elect to have a brain surgery then. The benefits might not be enough for you. But if you're unable to speak or type, that is a really devastating place to be in, because it really hinders your ability to express yourself, your autonomy, your independence. And I think that's the patient population who could be most helped by this type of device. And so we're still trying to figure out, what the prevalence is and what the incidence rate is. But in terms of people with chronic speech disabilities after a stroke, it's quite a bit even in just the US. I think from some studies, they said it was at least 50,000 per year who have some kind of long-lasting severe speech disability. Dysarthria is what it's referred to, where you lose the ability to properly articulate speech after a brainstem stroke. And that's long-lasting too. And then there are other traumatic brain injury. Some of these patients might also be reasonable candidates for the technology, depending on their level of ability after the injury and what part of the brain was injured. We can get speculative too. There's a lot of other types of conditions that may also be beneficial to have a speech neuroprosthesis to help these patients. This is highly speculative at this point, but for example, there are some individuals with nonverbal autism, autism spectrum disorder, that are nonverbal, who indicate that they can try to speak. They know what they want to say. They can imagine it. They can picture themselves saying it, but are unable to actually get it out. And it may be possible for our device to work for those people, because the key thing right now for our technology is that someone is able to try to say what they want to say. That is key, because we record brain activity from the part of the brain that normally controls the vocal tract, that controls our mouth, our lips, our tongue, our larynx. And so as long as someone is able to try to speak and they know what they want to say, they don't have language or cognitive deficits, then our technology may be able to work. And so there's a lot more research that needs to get done for us to understand the kind of extent of the technology. And I should also say, I don't think it's been published in a peer-reviewed journal yet, but there was an interesting kind of release from a lab in, I think, the Richard Anderson lab at Caltech in California, where they showed very, very small scale, I think only 8 words, but they were able to decode imagined speech. So this is very different from what we're doing. In our approach, the person has to try to speak. If they're just thinking it, it won't work. This isn't mind reading. If they think it, it won't work. They have to try to say it. But in this research, they show that people can imagine, really focus and imagine on certain words in a different brain area, not the area that we're in. They can kind of decode what the person was volitionally thinking to a very small extent. Again, it's 8 words, 8 different words, and only one at a time. But this is just to say that could expand the application to a different patient population. Maybe someone who's not able to think of how to form the words, maybe they have a type of aphasia. Perhaps this technology could work if they can envision the meaning of the word. This is, again, very far out there, but not necessarily impossible.
Yeah, thank you so much. It brought me actually to the research with the patients with disorders of consciousness, which were shown that there are misdiagnosed very often. And there are some studies and some devices, brain computer interfaces, that allow some of these patients to communicate, at least to say yes or no to different questions. So maybe devices like this would be able to help them to communicate more effectively. But of course, the question is about the invasiveness, especially when they cannot consent to be implanted with any devices, and probably which would be difficult in their condition. So
Yeah, you need to be really careful to understand if the person is truly consenting, but then also the device might make a mistake if you're using it to get the consent. And so I think there are ethical questions too that, people are starting to focus more on, which I think is good.
yeah, thank you so much. My next question is, what approaches have been used so far to help these people that you talked about to communicate? What have been available until now for them?
Right now, most of them rely on what's called augmentative and alternative communication devices, or AAC for short. So this is assistive communication device. These are assistive communication devices. A very common one is eye tracking interfaces. For many of these patients, they're still able to control their eye gaze very well, and they have a camera that is able to track their eye gaze location and allow them to spell out their messages. And this can also allow them to interface with the computer and to, go and send their emails, browse the web, do whatever they want to do on their personal device. There are some variants of this that may not rely on the eyes, but may rely on your head position if they have good neck movement. This can be a little easier to track. So there's one that you can wear glasses that have a video opaque marker, or I don't know exactly what kind of marker it is, but it's a special marker that a camera can easily track and knows exactly where that is. And so they can control the device by looking certain direction. There are other ones too, but these are kind of the more popular ones that I thought I'd mention. But all of them together, it's like extremely important, right? Because otherwise it'd be so difficult for some of these patients to communicate at all. So they're really, really important, but they all fall very clearly short of natural speech. And so that's why we still are pushing our approach and wanting to understand how far this technology can go. Because for us, that's still an ideal control modality for these communication devices, is speech. Something that would be more than just typing letter by letter, very slowly and laboriously. Something where you may not even need to look at a screen to use, you know. They could be watching TV or something and then try to say something and then their message would come out. So I think these little things would make a big difference. And I should also say, we are really trying to engage with the patient population to understand their needs in a more complete manner, to understand what their devices do really well and what they don't do so well. And I think it'd be really cool to make a speech BCI, right? A speech neuroprosthesis. Be awesome. But for it to be usable and for someone to like using it and want to use it and feel like they can trust using it, it has to be more than just cool. It has to be reliable and effective and intuitive. And so that's why we're just trying to engage with the patient population to understand really how to design this thing. If we continue to see good results, and then we think that this really could be translated to a clinical application.
Yes, absolutely, absolutely. And from what I see, there is a big complexity in the problem that you are trying to address, because there is research with patients suffering from ALS at those stages where they already cannot use eye movements to use eye tracker or other assistive technologies, and they're trying to use P300 speller, even sometimes invasive. So there are studies like this with implanted electrodes, but at certain stage, it stops working for some reason, and even this cannot help people to communicate And one of the explanation is that the brain activity is also changing. In terms of this project and with speech neuroprosthesis, that is also something that needs to be studied. What changes are happening in the brain of those people so that all this technology actually would be able to help and would work. That's a much bigger problem that needs to be addressed.
No, I totally agree. And I think that's why for conditions where there can be some cortical atrophy, so some, neuron death in the brain cortex, especially, of course, in the region that we're interested in recording from, that we rely on. That is really concerning. I agree. I think that needs to be further validated, further studied, because if all of the brain kind of patterns and pathways to control the vocal tract are gone, then that becomes a very difficult task for a speech BCI to restore. I think you may be referring to the one paper from the Burbaumer lab where they worked with someone who had basically complete locked-in syndrome due to ALS. And it was difficult. They did restore some communication, but it seemed very difficult. And it was a slow communication rate. But just to emphasize how important that study was, this was for a person whose commercially available devices, their eye trackers and such, stopped functioning, like they couldn't use it anymore. And so it got to the point where the brain-computer interface was basically their only way to communicate, at least if I'm understanding the article correctly. So I think it was an important work, but yeah, it's true that there's a lot to be studied to understand in what situations the device truly could help patients, because if the cortex starts to lose integrity due to their condition, I think it will make things harder. Yeah.
Even if to look at the responses that these patients have, P300 response, it changes in morphology dramatically in the course of the disease. Not always, but in some patients, it's very evident. So, yeah, many things to study. But now I want to get back to your project. Can you tell our listeners about the project that won the award in 2021? And also, what was the progression of the project and research that led to this project?
Yeah, so a lot of effort went into that, of course. Um, that was, I think, just even before the clinical trial started, really heavily informed by our work with the epilepsy patients. So they were kind of paramount to this, for us to study speech in the brain of these able speakers and to develop our algorithms and to know what works and what doesn't work, what brain regions are implicated. All these details are really, really key to enabling the clinical trial. And so at the start, when we recruited Pancho, Bravo 1, the first participant, and we implanted him with the electrode array, we had no guarantee that this was going to work at all. I'm not saying that we just went in blindly, of course, but it's research, right? Nothing was guaranteed. And so we had our informed hypothesis. And so the first thing we wanted to do was to understand what we could see. And we just had him try to say some words a few times while we recorded brain activity just to see, can we notice a pattern in activation? When he tries to speak, does it look differently than when he's just resting? That was the first, I guess, positive sign that we saw that we were really excited about, is that, hey, we're seeing signals when he tries to speak. And then we asked, okay, are they different for different words? And we looked at that and we saw, hey, they do look a little bit different. If he tries to say the word hello 100 times, and he tries to say the word goodbye 100 times, and we say, what's the average trace for the hello? What's the average trace for the goodbye across all the channels? And we just look at it and we see that there are differences. And so these are all really promising. And so we started there and then we kind of built up a little bit. And that's when we landed, okay, what is the proof of concept? How can we understand if this truly can work? We think it can now. And so how do we get there? How do we show that this is a real thing? For us, we settled on a 50-word vocabulary of very common words that would allow him to form sentences. So he would say, hello, how are you? So all 4 of those words were in the vocabulary. And what we wanted to do is by the time we've trained our models and are having him use the system, he would form sentences by trying to say the words in the sentence. He's trying to say sentences, and we were decoding the brain activity into those sentences. So we just had him say each of those 50 words many, many times. He's such an enthusiastic person. It's really a pleasure to work with. And yeah, eventually we were like, okay, things look good. Let's see, can we actually do this in real time? Can we have him try to say these sentences? And that's when we got our key, the core results for the paper. And to show, and we all could see it, everyone could see it, he could see it. He was extremely excited, by the way, when he saw it, that, yeah, he can try to say these sentences, and the device and the system is able to decode his neural activity into what he's trying to say. And then there are a few other follow-up analyses that are smaller around that project that were included in the paper, but that's the key results.
Thank you so much. And what was done in this area by other researchers in the world? And what was a specific contribution that you and your team have made that wasn't done before?
Yeah, so again, we talked about the cursor control brain-computer interfaces, so that's different. Putting that aside for a second, in terms of speech, anything speech-like, there was a series of studies, 2 studies primarily from the Gunther lab, where they had someone use a particular type of, it's a different hardware than we use. It's called a neurotropic electrode. It's a different design. I won't really get into it, but it's a different type of neural interface, but still needs to be implanted. To have someone control, it basically is a 2-dimensional space, but it's like a vowel space. So on one end, it would be like ah or ooh, and so it'd be continuously synthesizing the sound, creating the sound, depending on where they are in the space. I don't recall if they described if this felt like cursor control to the patient, or if this truly felt like something speech-like. I don't remember if they reported that and what they said if they did. But basically, they could control, like, maybe down here, oh, like things like this. And so this was very cool to see for someone who I'm pretty sure their participant was locked in as well. But I actually think that is really the only research in speech neuroprosthetics, and that's not really natural speech either. That's controlling a vowel space. But still, to my knowledge, that's all that preceded us in this space. And that's why we feel this was such an important step, because in our eyes, it kind of creates a new field in some ways. Maybe not like completely brand new that no one's ever thought of, but it shows that this type of thing can be possible. And now the question is how far it can go. And so we think our work was really important to show that, A, someone who hadn't spoken and been able to use speech to communicate for 15 years, the signals for speech are still there. So that's an important finding, because that was not a guarantee that the speech motor cortex would still have these robust and reliable representations of speech that can be observed and used. And so that's one. And then 2 is that it is possible to translate those into their attempted speech, into the translation of what they wanted to say. So those 2 things, I think, were kind of the key advances. Now, I should say there's a lot of labs, us and other labs, who have studied speech in volunteers and participants who are able to speak. So there's a whole world of research there. We're not the only ones to have done that. There are many labs who have investigated that and continue to investigate that, which is great. But in terms of with someone who is unable to speak due to paralysis, I think that it was basically the one pair of studies that I described with the valve control. And then I think also, I should mention, I think they also had some classification of vowel sounds. So I don't want to sell them short. They had a different paper where it wasn't this 2D control. It was more of a classification task where they're trying to decode certain sounds. But it wasn't on the order of full words. So ours was the first to show like full word that someone can try to say.
Yes, thank you so much. And also, your study, as I understand, did it in real time, correct?
Yes.
Because I'm sure that there were many studies on studying language and decoding, but they were not done in the real time. So it was post-processed already, data and possibilities.
That's a good point. Even with the epilepsy volunteers and other able speakers, not a lot were in real time. We had our study We had two studies, one with listening and one with listening and speaking, where we were decoding in real time. Yeah, sorry, I can't recall any others, but there have been since that, at least. I know. There's some groups that have tried to do, for example, speech synthesis in real time. This is Christian Herf's lab. They've shown that they're trying to decode speech in real time, and other groups have done this since then, but it's not as many, you're right, as some of the more offline investigations.
Yeah, so because it's more complex, so it's the next stage after things are figured out offline to already go to real time. So that's why it's again to emphasize the complexity of the work that you've done. And now speaking about all the technological development and in terms of hardware and in terms of software and AI models that are currently available for use. What of those innovative technologies helped you actually to complete this project? You also mentioned the electrodes that, a little different than in other studies. You used deep learning, as I remember, in modeling. So can you comment on that?
Yeah, for sure. There are so many things that went into this succeeding. I've talked about a little bit about the speech basic neuroscience and, understanding from our prior work and other groups' work, how speech is represented in the brain for mostly for able speakers. And that's been one thing. But yes, the hardware, we have these interfaces that have higher channel counts now, more densely sampling the brain surface. This is really important. And then, of course, the software, the algorithms. We borrowed so much from the world of automatic speech recognition, which is, like when you talk into your phone and it figures out what you're saying, turns it to text, language modeling, natural language processing, and of course, deep learning, machine learning, all this. It's very, very important. So our models did rely on deep learning architectures because the patterns are really complex. You have a lot of channels, a lot of signals sampled that not like extraordinarily fast, but definitely many, many times per second. You need to be able to model those dynamics. And it's a lot of subtle patterns. And this is what deep learning really excels at, or at least the models we're using definitely excelled at this, to be able to find things that you would not be able to tell by eye, perhaps, about the data to make inferences and to make accurate inferences. And then the other thing I would specifically call out is, yes, the natural language processing. This has been an extremely active field of research, and we basically just pulled developments from this field and applied it directly to our work. And so what I mean by this is like statistics of language. So when I say, how are you? The word doing is reasonably likely to occur, much more likely, for example, than the word glasses. There's all kinds of these sequence statistics in English. This is a huge area of research, and it's very, I guess, paramount. It's very fundamental to the language, I should say. And including these type of relationships, these sequential statistics, was really important in helping us get to a good accuracy level, a good performance level. Because, of course, the neural BCI, if I haven't said it so far, I'll definitely say it now. It's not perfect. The speech neuroprosthesis is not perfect. It does make mistakes. So we were at about 75% accuracy in that first paper. And so having this model of language to help out was very, very important. So yeah, in summary, there's a lot of advances in machine learning that we really rely on. And I think it's really cool that we can kind of see these advances. There's so many labs working on this, right? And companies too. And we can see these advances and say, hey, can we use this for our work? Is this a reasonable thing to do? And so that's been really helpful. Yeah.
Yeah, absolutely. And to what you mentioned, we probably see in real life, even in our Google Mail, when they're providing already certain phrases when you just start typing. Yeah, so it's predictive model of what our language can possibly be. So just to simply explain.
Oh, yes. That's a really good point. That's right.
Mm-hmm. You also mentioned that this technology of improving spatial resolution of what you are doing by using a large array of electrodes that are much smaller, maybe microelectrodes. How do they differ from the ones that are usually used for epilepsy patients for their pre-surgical workup?
Yeah, so what it seems is not uncommon, or at least it was a few years ago when I was working more with the epilepsy patients. But you can sometimes have these higher density electrode arrays. So these are ones that are covering a large portion of the cortex and also sampling, very kind of close together from neural populations under these electrodes that are kind of more close together. But sometimes for clinicians, it's not terribly important to have that level of resolution. It's the nature of the pathology, it's the nature of the epilepsy that you may not even be able to resolve super fine grained precision where the seizure is coming from. Again, I'm not a medical doctor, and I'm not a neurologist, so just take all this with a grain of salt, please. But from what I understand, it's the needs of localizing the seizure location are different than the needs of driving a speech brain computer interface. And so what may work very well in this kind of epilepsy treatment situation may not work as well for speech decoding, because we might have, for example, in the speech motor cortex, two neural populations or subpopulations, I should say, that are very close to each other, but encode slightly different things. Like one may like the sound ah, one may like the sound sh, right? And even if they're really close, again, there are exceptions to this because we do see some level of organization of the cortex for different articulatory features. But still, even ignoring that, you still might have two electrodes that are really close together that have slightly different tunings. And that information is useful. So that's why we tend to prefer higher density neural interfaces. I think a lot of groups, a lot of research labs, a lot of companies are also understand that you really just want more data. You want more high quality data from the right brain areas. And that's what gives you the best chance of success.
So, how many channels, how many of those sensors did you use for this particular patient for your study with the Pancho patient that you mentioned?
So we used 128 channels. This covered about 6.7 centimeters by 3.5 centimeters. Like that's the size of the array. And so it's a 16 by 8 electrode arrangement with 4 millimeter center to center spacing. So 4 millimeter electrode pitch.
Yeah, and I'm very curious also, how did you know where exactly you want to implant that electrode array? How did you find that area?
So what is common to do, that's a great question, is to do functional magnetic resonance imaging, fMRI. So you have the patient go in an fMRI and try to do some speech tasks. And then you can kind of see roughly what brain areas are activated during attempted speech. I would say that this is a very reasonable thing to do. I think for us, though, it's more confirmatory for us. We just want to make sure that we're seeing something because we basically know where we want to target. Because this is informed a lot by not only our research, but many labs' research and many doctors' research throughout a long time that implicated this brain area, which is kind of the ventral to middle, precentral gyrus, postcentral gyrus. A lot of neural populations here that have been implicated in speech processing. There's also Broca's area and the inferior frontal gyrus, for those who know their brain anatomy. But we've actually found, I think in a lot of our lab's research, that it's really the pre and the post-central gyri that are the key players. And so that's where we're trying to focus on, especially the precentral gyrus. If we looked at a brain map, I could point it out, but otherwise it may be hard to follow along, I guess, if you're not familiar with this. But I guess the short answer is just from prior research, we know where to expect evoked responses related to speaking. And so that's where we targeted.
Many people often ask, especially when they hear about implanted electrodes, how long can they stay in the brain? And maybe in your particular study, how long have it been?
It's a great question. Yes. So I'm excited to share that our first participant, Bravo 1, Pancho, he has just passed the 4-year mark with our device, which is really a promising landmark to pass. And our signals still look good. We haven't seen a lot of channels drop out. We don't get bad channels that are just no longer functioning. So overall, I think very positive. it's possible that these devices, this type of approach can really be reliable and for long-term use. You don't want to show it in just one person and then say, okay, it's good to go. So we need to study it with more participants. And that's why we're still actively recruiting. But to hit the 4-year mark is a pretty big deal for us. And to see that we're still getting reliable signals, we're still pursuing research projects with Bravo One, and yeah, very encouraging.
Yes, absolutely. So, as I understand, you are still continuing the project, and what does it entail for a participant? How often does he come to the lab? How actively he is participating in the studies? How all that works?
For sure. Yeah. I mean, I should say too, I haven't mentioned it yet, but the clinical trial is done with a collaborator as well, also at UCSF, Dr. Karanish Ganguly and his lab, because we're looking at speech, of course. But the other aspect of the Bravo clinical trial is non-speech motor control. So things like, hand and arm reaching, cursor control, these things. So our collaborators, they also work with Bravo One. So he's fairly busy. We go to him though; he doesn't come to us. So we worked with him a little bit in his residence, but he didn't like us storing all of our equipment there. So we rented a office room nearby, just a small office room, nothing fancy at all, just a typical office room. And we just set up there. And whenever we work with him, that's where we go. And we, bring him to the office, and then we do our work with him. And so he likes to work basically like 5 days a week. He says sometimes he's sad on weekends because, he doesn't have the work to do. He doesn't get to talk with us. He's just such an incredible person, and he likes to contribute in this way. He feels like it's quite meaningful for him, which we definitely like to hear. But of course, if he's ever like, I need some days off, we just no worries whatsoever. It's all about how much he wants to do.
Yes, thank you. It's just so good to get the insight of the project and see how it really works. What were some of the biggest challenges you faced while working on this project, and how did you overcome them?
Well, one very big challenge was the COVID-19 pandemic and all the lockdowns and stuff. We had to basically halt our research for a long time because that's kind of perhaps not the answer that you were looking for, because there's a lot of other challenges. But just when I think about it, it's like we had to go a few months without working with him. It was still in the early phases of the project, within the first year, basically, when this all started to go down, or like right after the first year mark. And so it was a little bit difficult to keep the data collection going eventually and to get back into it, but it wasn't catastrophic or anything like that. I would say some of the big challenges is just trying to understand that we're doing, there's so much that's unknown, and there's so much that we have to figure out ourselves in terms of what's the best way to do these tasks. What's the best way to analyze the data? What's, all these things together. It's just so much like, I don't want to say trial and error, but you'd have to really make informed guesses and set up your informed hypotheses and be able to adjust really quickly. You have to stay very kind of nimble, if you will, very flexible as you try things and adjust, because it's very exploratory, right? This is an early feasibility study. There's a lot that we're just figuring out for the first time. So I would say that is one of the challenges. Like, it's just kind of like making plans, and you make a plan, it sounds great, and then you test something, it's like, oh, this plan doesn't work. We have to completely readjust. And that can be a challenge. So maybe I'll just leave it there. There are some other ones too, but they want to take up all of our time talking about all the difficulties.
Yes, thank you. And as you were saying that there were a lot of exploration, you got some significant results. What new windows of opportunities did this result open up?
This was the first time that anyone had really seen this. I think a lot of researchers in the field suspected that something like this might be possible, but this was still the first confirmation that it is. And so I think that opens up a lot. Because, by the way, before we had this result, a lot of papers on this type of topic, including ours, by the way, it's like, how do we motivate them? How do we motivate these studies? A lot of the motivations was, one day this might be helpful for someone who can't speak, because you can have a neuroprosthesis and they can use XY result that we show here, and maybe it'll work for them. And we say this, other labs have said this, and so forth. I think it's really valuable to show that, like, Now we know that this actually is possible. And so we can kind of motivate this type of research even more. I think one key is understanding what will translate fully from able speakers to these participants. And unfortunately, one challenge is that there's likely a lot of variability between people. I mean, not even people with the same condition, there might be a lot of variability. The array placement is going to be a little different every time. Maybe the array you use is different as well. So there's a lot of sources of variability, and I think those are kind of open questions. But in terms of the opportunity that's afforded by this achievement, by this milestone, I think it's very significant because now we know that, for example, it may not be totally unreasonable to try to replicate all of our results with able speakers like in this patient population. That's not an unreasonable thing to do, or at least many of the results. And so I think this opportunity is there now because of what we found and what we showed in that paper.
Yeah, thank you so much. And how do you continue this project? You already mentioned the 2022 BCI Award submission, and I saw the paper by Metzger, the first author in Nature Communication. Maybe you can talk about that.
Oh, of course. Yeah, that was a very important follow up, in my opinion, at least. Of course, I'm a little biased because I'm also one of the co-first authors, of course. But I think that paper is important because it really spelling, we want ideally to move away from spelling and to just have someone, if someone who's paralyzed and can't speak wants to say anything, they can just say it. That's an ideal case. But for now, spelling definitely does have a place. Almost all of the assistive devices rely on spelling. And spelling really is a great way to get to a completely flexible vocabulary size, a full range of meaning to convey through text. So when we showed that in this work, just very briefly, we had Bravo 1 just silently say, I think I mentioned earlier, like the NATO alphabet to spell something out. So if you wanted to spell cat, he would say, silently. So that's another advance. This is silent speech now. He doesn't even have to try to vocalize. He's just silently moving his mouth, what we refer to as kind of miming or a silent speech attempt. So it's like attempting to speak, but without engaging your larynx, without voicing. And so he would silently try to say Charlie, Alpha, Tango to spell cat. We did this because it's kind of the same reason they were invented. It was, it's a pretty nice translation of the motivation. So the NATO alphabet was invented because if you're communicating over a noisy channel, it can be hard to make out single letters, C versus V and P, all this stuff. And so what is better in noise? Well, you have a little more content. So alpha is more content than A, Bravo is more content than B, and then you have these really differentiable words that represent the letters. If you view the neural space as kind of a noisy channel, because there's a lot of brain processes that are going on that are irrelevant to the attempted speech. There's a lot of, if you will, background noise. That also really well motivates the use of the NATO alphabet instead of just single letters. And that's why we did it. And we also show in the paper that it does work better than single letters to do the NATO alphabet. So our hypothesis turned out to be true there, that we confirmed. And so the goal was to just enable him to spell words now from 1,000-word vocabulary. So he's spelling sentences using the NATO alphabet and trying to say them with a vocabulary size of over 1,000 words. So much, much more than the 50 words we started with. And our accuracy was at about 90% for this and about 6 words per minute. So again, it's not nearly as fast as we can speak, but pretty reliable level of accuracy. And I think an important validation because I can't imagine, at least in the first iteration of any clinical application of a speech neuroprosthesis that would not give the user the ability to spell something out. They have some word or some name they want to spell that's atypical or uncommon. I think it's really useful to have that approach. So that was an important next step for us.
Yeah, and I'm very curious about what possible implications the results of your studies can have beyond the application for speech and communication.
Yeah, it's a very thought-provoking question. I may answer this slightly differently, which is communication is one thing, but speech is also can be really good for issuing commands, for example. So maybe I'm not actually trying to say something to someone, but maybe I still want to control some aspect of my environment. I mean, this is like when you talk to your phone to tell it to set an alarm, or if you talk to your like home systems to turn the lights on and off or change the temperature or whatever you want to do, it's useful to have speech to be able to do this. And you can imagine, for example, let's say that you had a robot arm. Now, maybe you want to control it. If it moves forward, you want to think, okay, move forward. That's one way of controlling it, like on a low level, a fundamental level. But maybe you don't care exactly how it does its thing. You just want it to pick up a cup and bring it to your lips so that you can drink and let you drink from the cup. So maybe you can issue a command to do that via speech. So slightly different question, I suppose, than what you asked. But if I were to go back a little bit more, it's like, what are the other implications of this? Maybe in the future, this is very future facing, but there are, speech language pathologists who do speech rehabilitation. And it could be really helpful, for example, to have a neural interface for that as well, to understand the neural signals when someone is trying to speak. You might be able to get some new insight that could help rehabilitation. So that's one example. And then I think of the hardware itself. I mean, there's lots of opportunities. There are a lot of different types of neural implants. For us, we're very optimistic about the long-term prospects of ours. And so if our neural interface truly is, let's say it's a very viable method to getting a long-term BCI, a neuroprosthesis, then I think you can have lots of other applications. You can do stimulation through this interface. You could have it for motor, not just speech. So I think the hardware itself, and that's one of the primary points of the clinical trial actually, is to assess long-term safety and feasibility. So if we can show that our implant is safe and reliable over a long period of time, I think that does have other implications beyond speech. That has a lot of implications broadly for brain-computer interfaces.
Mhm. Yeah, that's very interesting because I didn't realize that you also made the implant. So was it made at university? What type of implant is this?
We kind of designed these arrays, like the specifications that we needed, but the actual array itself was fabricated by PMT Corporation, which is a medical hardware corporation. So we have the implant itself, but how do we get the signals from that? So right now, there's a metal tube, basically a feed through that is also implanted in the skull. So if you have this, the skull is here, you have this metal tube that's here, and the array connects to that. And then we connect to it here outside of the skull. And that is made by BlackRock Neurotech. And they basically took the array and they attached it to their pedestal, that was what we call it, that's feed through. And that's the final product. So it's kind of a hybrid implant. It's like a custom hybrid implant that has the array from PMT and then this feed through from BlackRock. And then the hardware we use to process the signals, the first few processing steps are also made by BlackRock.
Mhm. Yeah, thank you so much for clarifying that. And again, it demonstrates the truly collaborative nature of this type of research. I'm very interested in the field of neuroeducation. And in neuroeducation, we have a lot of neuromyths, like that we're using only 10% of the brain and, others like this. I'm sure there are a lot of neuromyths or misconceptions associated with the implantable devices and speech decoding specifically. So maybe you can talk about some misconceptions that you've noticed and how do you address those misconceptions in your work and research?
Well, by far the biggest one would be that our work is mind reading. That's definitely the biggest misconception. And that's been very prevalent. Just to relay a brief story, because this actually happened to me, is during my PhD, I did this project where it was kind of really simple compared to what we're doing now. We had patients listen to sentences. So it was 10 sentences, pre-recorded audio files. They would hear a sentence, we'd record the brain activity, and then eventually the goal was to show that we could decode the sentences in real time from the brain activity. So it was a 10-way classifier. There's only 10 possibilities. And we would just show that we could predict which sentence they heard in real time from the brain activity. Okay. So a pretty straightforward little project. Definitely took a lot of work, and they got published. And one morning I woke up and I got a bunch of emails asking if I could be interviewed for my mind reading device. And I'm like, what is going on? I don't understand. And I respond, I'm like, what do you mean? And they're like, well, there's these articles and you're even quoted in them. And I go and look and oh my goodness, there's a bunch of tabloid articles that said that I had a mind reading device. And some of them even, they quoted something I said in the paper. I talked to this media outlet and said this to them. And it was really kind of alarming. It's like they didn't understand that this is just decoding what someone heard. And furthermore, I mean, it got to the point, I won't say the name of it, but a very big American news group that you would recognize contacted me and offered to fly me out to demonstrate my mind reading machine, live in their studio for one of their episodes. It was just absolutely so bizarre that so many people just like didn't even read more than a few words, it seemed, of not even the full abstract, it seemed, because even the full abstract, people would have understood that this is not just some hat that you can put on that will read your mind. This required surgery, and it was just classifying 10 sentences. And so that's a very clear example of this. But there's been, throughout a lot of our other publications, if you look at some of the media reception or social media, a lot of times, and, I don't really blame people. Not everyone's an expert in the field. They don't work on this all day. So I know that it can seem like mind reading, especially when we move to the silent speech. It can seem like mind reading. And I get that. But it's super important to emphasize it's like the person has to try to speak. If they just think, it won't work. I mean, that's a really hard problem. And even this other lab that I told you about in Caltech that is able to show someone can think of words very intensely, they can decode, 8 different words. That too requires effort. It requires volitional effort and focus. No device is going to read someone's inner thoughts, your private internal monologue. I'm not saying that that's fundamentally impossible, but I'm saying I've not seen anything that suggests we're close to that at all. So I just want to emphasize that for everyone. It's like, you're not going to have, walking by somewhere and someone's reading your mind. Like that's, maybe check back in 100 years and maybe something like that will start to seem more feasible. But, I can't predict the future, but all I can say for now is that there's no evidence that I've seen that suggests this is remotely close to possible.
Mhm. Yes, thank you. One more neuromyth got busted.
There
So,
we go.
thank you. Speaking about the future, what are your future plans? What are you going to do next in your research?
Yeah, so we have 4 main points of focus for what we want to do moving forward. One is we want more expressivity. So right now, patients are communicating via text, but there's a lot that's conveyed, a lot of meaning that's conveyed in speech that's not readily captured in text. I mean, there's so many what's called like prosody. There's so many cues of meaning that you can't get something's written out. I mean, I think most people have texted something or written something on a social media, like typed it out, and it's been misinterpreted or something like that because it can be hard to truly understand all these things. I mean, one very simple example, just telling something's a question. A lot of times a sentence that's not a question ends like this, and a sentence that is a question ends like this. You have pitch cues and you have speaking rate cues, all this information. Okay, so how do we restore that? We've shown with epilepsy volunteers that you can synthesize speech directly from brain activity. This is with able speakers, and you can actually create the sound, the speech sounds from brain activity. And that is one way, that's an approach to getting towards this, of restoring more expression. Okay, so that's one thing. Second thing is there's nothing that says that this should only work in English. We might be able to allow people to communicate in other languages other than English, as long as they're vocal languages, spoken languages. But that's one thing that we're also quite interested in. Number 3 is there's a lot of improvements that can be made to the hardware. More channel count. Eventually, you want a fully implanted system that doesn't leave, because if you have this metal feed through that I described, that's kind of an infection risk. We work really hard to keep that area clean and to maintain it. But ideally, you would have something that's fully implanted so the skull can just be healed completely and not have anything penetrating through it. and then you can communicate wirelessly to the device and power it wirelessly. So this would be a huge step forward. That's something that we're interested in. Lastly, and perhaps most importantly, actually, is getting more participants. We have to show this in more than just one person. So that's a huge focus for obvious reasons. Like if we're going to say that this is useful and this can be used to help people, it has to be in more than just one person.
Thank you so much. And how willing are people to participate in this type of research? What's your experience?
Yeah, it can be quite difficult. I mean, it's a huge ask, you know. People who are in a vulnerable state, people who don't have a lot of their autonomy, people who have they have their own real life struggles. And we're asking them, hey, would you like to basically spend 5 days a week working on research that will not immediately benefit you, but will hopefully benefit field of science overall? That's a big ask. It does seem like there's quite a few people who are interested in brain computer interfaces in general and like who are open to the idea of one, but not just for research. It has to be something that would help them, and it's totally understandable. To be honest, we wouldn't want a situation where we get someone who's kind of on the fence, right? We are very careful to fully explain like just everything that's involved in the trial, and for them to understand that they have the right to get explanted, have the device removed at any time in the trial. Every participant will have that opportunity. So it's not like anyone's trapped into a long commitment, but still, we want them to understand this is a lot to ask of someone. And we also have a lot of exclusion criteria to make sure that the person's a good fit, in terms of other conditions they might have that might preclude their involvement in the trial. So it can be difficult. The short answer is it's quite difficult to find participants for this type of research. But we're optimistic that we're going to be able to show these results in more people in the future.
Yeah, absolutely. And your papers and everything you tell about this project, I hope it will make things more understandable for your potential participants. And
Yeah, that's a really good point.
how do you see this field of speech neuroprosthetics, let's say 50, maybe even 100 years from now? You already mentioned certain things, but maybe we can summarize everything. Mhm.
Yeah, well, I'm hopeful that someone who needs a technology will have more or less full autonomy where they can communicate as if, just like you and I can communicate. That's the goal. So they would be trying to say their sentences and it would come out in their own personalized voice. And that's made possible by a lot of advances in this kind of speech research outside of neuroscience, machine learning, and things related to speech. So that is a major goal. We want people to be able to express themselves naturally, just like you and I can express ourselves via speech. And then we also want to make sure that they can control their devices. So they have a full ability to interact with their personal device through the interface. Yeah, and something that's reliable and long term, something that's fun to use ideally, so it's not a burden and it's not tedious or fatiguing, something that's very natural and ideally effortless. Those are kind of the goals. And I think in 50 years, I think we can get pretty close to that. I'm fairly optimistic about that.
Yeah, thank you so much. That's a beautiful vision, and I hope it will become a reality. Couple of questions about the careers. One question is about the BCI award. What do you think made this a winning project, and what would be your recommendations for those who are planning to submit their project for BCI awards?
Well, I can say I was also the judge in the following year, by the way, so I have a little experience as well in just judging some of the top projects. I think really, like the best advice is I wouldn't recommend tailoring a project to the BCI award committee. I mean, maybe this is not the right thing to say, but this is my take at least. Really, the motivation should come from your research, and you should ideally have a question that you're interested in, and really just give it your best shot to address that question and to do the research that you think is important and valuable. And then when it comes time to submit, all you have to do is just make sure that you convey your results meaningfully and concisely and clearly in your submission. That's really the only advice I can give for the submission part. I think that really just finding a problem in the BCI world that you think is meaningful and then trying to address it. That's most of it.
Thank you. And what is one skill you couldn't accomplish this project without?
So there's clear things that I could say, such as, you know, managerial things or machine learning techniques or these types of things. But to give something I think a little bit more informative, I would say one of the roles that I played in terms of developing the software approaches, the algorithms, was again to develop and maintain this real time interface. And for me, a skill that was really important was patience and attention to detail. This involves, even though it makes every task a little bit longer, it involves like investing in the future. So, like future proofing your methods, making things really flexible and robust because basically my infrastructure is what everyone else in the team had to interface with to do what they needed to do. So I didn't make the classifiers that were used in the paper, the neural models, the deep learning models. I didn't make those. The speech detection models, I didn't make those. But I designed the infrastructure so that those could be slotted in and operate as they needed to do. And to do that, it meant that I could never be satisfied cutting corners in what I was writing in terms of the code. I had to make sure that everything was very flexible, that if someone needed to change something, okay, they could change it. It's very clear, like what are the inputs and outputs. It's just very rigorous, I would say. And it made everything take longer, but it meant that I didn't have to go back and redo things every time and that things were clear. And this, it's a lot of upfront cost, but it buys you a lot of delayed value. And so I think that was a skill that was really important for me to hone and kindle as I kept contributing to the project.
Mhm. Thank you. And what advice do you have for individuals interested in pursuing career in speech neuroprosthetics? And what skills or areas of expertise do you think are most important for success in this field?
It's very valuable to be really knowledgeable about the state of machine learning and just keeping up with the advances. I mean, there's kind of new advances every year in machine learning. And I think there's a lot that can be applied to speech BCI. And so that I think will continue to be valuable. In addition to that, I think there's a lot of ways, and so many different varieties. I mean, even people, for example, with material science experience, they might have some knowledge that can help make a really good brain implant, a really good neural implant hardware that can really help enable the future of speech BCIs, right? So even things that you might think are tangential to speech neuroscience and speech BCI research, such as material science or like microfabrication. There are a lot of industry jobs right now for companies trying to make the latest and greatest brain implants that need these types of skills. So I would say there's a lot of variety right now in this. I mean, also clinical experts, regulatory experts, people like clinical research coordinators, those who can actually maintain clinical trial and help out with those duties. I mean, there are so many avenues for a contribution to this field. Speech language pathologists, you might have some really interesting insights that can be helpful. I would say if you want to work on the algorithms, of course, you need machine learning, but there are definitely other avenues as well to kind of contribute really future facing to this field.
Thank you so much. And you mentioned to stay up to date in the field. So, how do you stay up to date with the latest advancements in neuroprosthetics, neuroengineering, and what resources do you recommend for others interested in this field?
Well, I'm lucky. I have a team of really smart and bright students, postdocs, etc., keeping a good handle on what the new developments are and different things that might be applicable to speech. I also try to keep up to date myself, but it's much easier as a team because you can easily miss things. And then I would also say just review papers, you go to conferences, listen to talks, all these things. Conferences can be a really good way to stay in the know about what's the latest in a field. And so I think all of these together really help to keep up to date.
Thank you. And the name of our podcast is Neurocareers Doing the Impossible. What was one thing that seemed to be impossible that you made possible in your studies, in your research, and how to make the impossible possible?
Well, I guess things may seem impossible until they then seem possible, right? I just think that going into this project, not knowing if it was going to truly work with all the challenges that were there and coordination, just to get the full system going and to understand if what we're seeing is real or if there's an error, all these things in just this brand new research area, it's going to be very daunting. And, I don't know if I would use the word impossible, but well, clearly it isn't. But, we knew it was going to be very, very hard. And I think part of it is just really understanding how to step back and view it in these kind of like, what do you know? Like, in these kind of bite sized pieces. Like, what do we know? What can we do? What are the tests that we need to do to get on our way? Targeting the impossible, maybe that will work. But sometimes I think it's also important to take a step back and be like, okay, well, what aspects of the impossible do I think are actually possible? And then as you start to work through those, then maybe you can finally get to where it's like the impossible doesn't seem so impossible anymore. There are some things that seem fundamentally impossible, maybe by the laws of physics or whatever. But other than those, I mean, it's really important to truly try to understand what makes something feel impossible, what aspects of it might be more possible than others. And that's how we approach the clinical trial.
Thank you so much. And what would be the best way for our listeners to learn about you, your projects, and get in touch with you?
I'm not very active on social media, for better or worse, but I do have a Twitter, and it's at David Moses. So that it's AT and then David Moses actually in the handle. And then we do have a Edward Chang Lab website that you can also go to see some of the latest publications and team members and everything. Those are probably the best ways at this time.
Thank you so much. And we will add this information into our podcast notes as well. Is there anything else you would like to mention to our listeners before we wrap up our podcast today?
I would just recommend, if you are interested in something, a lot of people are pretty nervous about reaching out to folks, like just kind of cold email, if you will. But I think at least in academia, for researchers, you have very little to lose. Like if you're someone who's interested in some type of lab's research or something, just reach out to them. The worst thing that they do is they don't respond, and then maybe they're just busy, I don't know. But it's worth a shot, It can be really helpful for you to be able to get someone's perspective on certain things. Just reach out to the expert. So that's just something that I would recommend for people to keep in mind.
Thank you so much, David. It was a pleasure to have you on our podcast. I'm sure our listeners learned so much and enjoyed this conversation. I wish you all possible success in your studies, and that what you are talking about from 50 years from now and further would come even earlier, and we all would be able to witness that. Thank you very much.
Great. Thank you so much, Milena. Thanks for having me. The pleasure was mine.
Are you a fearless pioneer in the world of brain-computer interfaces? Do you have an amazing project that's pushing the boundaries of what's possible? Then we want to hear from you. The International BCI Award is one of the biggest and most prestigious awards in the BCI world, and the deadline for submission is September 1st. But don't worry, you don't need a top-notch budget or equipment to be a nominee or a winner. All it takes is a great idea and the determination to make the impossible possible. So, submit your project now at bci-award.com or find the link in our podcast notes and join us on this incredible journey to explore the world of BCIs. And make sure to listen to our upcoming BCI Award Neurocareers podcast series for tips and tricks on creating a successful submission. Who knows? You might be the next nominee or winner of the International BCI Award and proudly showcase your nomination on your resume to impress potential employers and establish a successful career in neurotechnologies. But don't stop there. If you are looking for more guidance on succeeding in Neurocareers, book a free consultation with me, your podcast host, Dr. K, at the Institute of Neuroapproaches. So, what are you waiting for? Let's make the impossible possible together.